I talked about discounting. Now I'm going to talk about uncertainty, and I have 3 chapters to cover. We're still at the sort of basic point that if you don't care about the distant future, faraway lands, or remote probabilities, there's no need to care about climate change. And I'm going to talk about remote probabilities in this hour, and then the first hour this afternoon I'm going to talk about faraway lands. So your standard for micro will tell you that you should not try and maximize your utility, but rather your expected utility. And in this framework, what we should be focusing on is not our damages or the social cost of carbon, but rather the expected social cost of carbon. And the expectation is, of course, if you have a discrete number of alternatives, it's simply the sum over the impacts in those alternatives, that is the S, where S denotes state of the world, and then P sub S is simply the probability of that occurring. I showed you the CDFs of the social cost of carbon, and there is a strong suggestion that the bad tail is heavier than the good tail, that is, things are right skewed, and they're asymmetric in the wrong direction. The uncertainty is quite large, right? It is another thing that we talked about. And that is what you see happening if we just focus on the characteristics of these probability density functions or cumulative distribution functions. You just look at the best guess for 3% pure rate of time preference, that's 27. But if instead we're looking at the mean, the average, then that is 40. So we should not be focusing on what is sort of our best guess of the impact that climate change should be doing, but rather we should be focusing on what is the impact in expectation. It makes a difference, right? And it might make a considerable difference. So it's 27 versus 40, 90 versus 210, 240 versus 590, 30 versus 50, 24 versus 34, right? So there's always a considerable gap between the mode, the best guess, and the median. So you would expect that if we redo the analysis of what should we be doing about climate change, what is an optimal climate policy, if we redo that under uncertainty, then impacts would actually increase. Or optimal climate policy would actually be more stringent. This is incorrect. We should not look at the expected damage at all. We should be looking at the so-called certainty equivalent damage. What is the difference between the two? In expected damages, we're looking at the expectation in money. D is given in money, ED is given in money, and we just assume that if we're doing a welfare calculus, then we should be adding up dollars. We shouldn't. We should be adding up utilities. What matters is not how rich people are, but what matters is how happy people are. So really what we should be doing is taking expectation not over dollars, but rather over the utility, weight the utility by the probability of occurring. We are interested in the damages, so we should then take the inverse utility to get back to the damages, measured in dollar terms or in euro terms. That's the definition of the certainty equivalent damage, and then the definition of the risk premium is the difference between the two. The difference between certainty equivalent damage and the expected damage. Now, you might wonder what I'm on. What am I doing here? Instead of using the damages, I stick in the utility function, and then I take the inverse of the utility function. So those two operations should just cancel, right? Well, do they? Well, by Jensen's inequality, they don't, right? But do they approximately cancel? I think this is best done with an example, rather a numerical example, rather than just math. So let's look at the situation where we are the uncertainty is relatively tight. Either we suffer an impact of 10 euros or we suffer an impact of 20 euros. And then the expected impact that we suffer is 15, right? You could have worked it out. Now suppose that we start with an income of 1,000. So the relative impact is 1% or 2%, and we have logarithmic utility. So the log of 1,000 is the base income minus 10. So the log of 990 is 690, and the log of 980 is 689. We get the average of the two, and we have a loss, or a utility of about 689. We compare that to the utility of 1,000, that is log 1,000, 691. We take the difference between the two. We compare that to our initial income, and rework what is the equivalent, the utility equivalent income loss, and we find and certainty equivalent damage 1501. So you were justified in thinking, what is he on about, right? If you do the straightforward calculation, then we find that we should use 15. If you do the complicated calculation, then we find that we should have an impact of 1501. But the difference is 1 cent on 50 euros. 15 euros. That's pound here, but it is more 2 euros. Right? You can really evaluate this. What happens if our base income is not 1,000 but 100? Then we have 454.38. This is what the average is 442. We work the whole thing, and we find that risk premium is 15 cents rather than 1 cent. And we see a slightly bigger deviation between the expected damage and the certainty equivalent damage. But it's still not something, given all the other uncertainties that we're talking about, something that you can be able to write home. An alternative thing we can play with is that our impacts are not 10 versus 20, each with 50% probability, but rather that 10 versus 99, each with 50% probability. If we evaluate that along an income of 1,000, then we find the expectation here is of course 54.5. The certainty equivalent is 55.5. Still, we're talking about a risk premium of about €1 in 55 euros. It's still relatively small. But if we now go and evaluate it along an initial income of 100, then things start to diverge. And whereas our expected damage is 54.5, our certainty equivalent damage is almost twice as large at 90.5. And now we have driven a wedge between the certainty equivalent and the expected damage. And this all follows immediately from the curvature of the utility function. So if you have a logarithmic utility function, it goes like this. And as long as we're sort of in this bit and we're moving around a little bit in here, things are approximately linear. But if we now run the risk of pushing our income from somewhere here all the way to almost zero, that is what we're doing in this scenario. Right? We're pushing our income from 100 to 1. We're losing almost everything. And then we're at the very steep, the very nonlinear part of our utility function. And then it starts making a big difference whether we're calculating in dollars or whether we're calculating in utility. Because there the loss of income here is 99%, but the loss of utility is from 450, let's see, it's more than 450 to 0. And of course, if we go to more than 99%, these numbers become negative, and we start losing a large amount of utility. So what do we see from these calculations? First, if we are talking about losses that are relatively small, relative to our income, we can just do your standard, let's calculate the expected utility. And that becomes more pronounced as we grow richer, right? The certainty equivalent calculation does not add a whole lot. There is a difference between this one and this one. But if there is a chance that because of climate change we're going to lose most of our income, and that is of course, when that risk is much more pronounced at the lower end of the income distribution, then this particular risk starts dominating the welfare calculus, and things become extremely nonlinear, and you should be very, very careful in the way you do your utility calculation. And if this is a realistic prospect, or in fact a prospect that has a non-zero probability, then your calculus in terms of dollars becomes wrong, and you should really, really switch to the formal and appropriate calculus in utility. And in a way, this is very similar to what we did with the Weitzman gamma discount. Do we take the average of the discount rate, or do we take the average of the discount function, the discount factor? And the discount factor is, of course, what enters into your utility function, whereas the discount rate happens to be the parameter that everybody's talking about. But it's actually not the parameter that matters. And the same is here, the same is the case here. Very easy to talk about impacts in terms of dollar numbers, and let's just take the average of them. But of course, what really matters is what does this do to human well-being, and that is what we should be taking the average over. I'll come back to this afternoon. Chapter 2. Let's start with a simple problem. Static, we know all our parameters with certainty. Then the first order condition for optimality is that the marginal cost equal the marginal benefit. Right? We've done that. If we have a dynamic problem, but we know everything with certainty, then the first order condition for optimality is that not the marginal cost, but the net present value, or the marginal of the net present value of the costs, should equal the marginal of the net present benefits, and nothing much has changed, right? We just inserted two words. Marginal cost, we speak about marginal net present cost, and instead of marginal benefits, we speak of marginal net present benefit. So the equation can get very hairy, but the principle is the same. If we now introduce uncertainty, we move back to the static problem, then essentially we should be equating the marginal expected cost to the marginal expected benefits, or rather the certainty equivalent, right? But again, nothing fundamental has changed. Instead of equating marginal cost to marginal benefits, we insert the word expectation or certainty equivalent, and we say marginal expected cost equal marginal expected benefits, and we introduce, if we move from static to dynamic, we introduce aggregation over time. So rather than having the DBC, we have the sum B of the DBE, we have the sum B to DE, and if we introduce the marginal, or if we introduce uncertainty, we replace DB, DE with the expectation operator, which is the sum over B, DE, right? So nothing has changed in principle. We just introduced an integral into our first order condition. So now let's put the two together and look at dynamics and uncertainty. From the things that I've just said, what you would expect is that really what we need to do is replace marginal costs with marginal expected net present costs. We introduce two integrals, or two summations, and ditto for the marginal benefits. Marginal expected net present benefit. And just the notation gets out of hand, and things get ugly in terms of the mathematics, but conceptually nothing has changed. That is what you might think, and that is what some people have claimed. It is not true, because things fall apart if there's irreversibilities and if there's learning. If those two things are present, then we should do more than just insert the two integrals or the two words expected and net present. Now, why is that? Why is irreversibility important? Irreversibility is essentially that if you make a decision now, you're stuck with it. And it's not in the case in the sense that you make a decision now and your decision can't be undone, but the decision has consequences for the future. If I am a farmer, I decide to plant wheat this year, then that does not affect my decision what to plant next year, because the wheat has been harvested. And next year I could decide to grow wheat or maize or whatever. So that is not an irreversible decision. It is irreversible in the sense that I can't go back and make a different decision, but it's not irreversible in the sense that it does fundamentally affect my future decisions. If I'm a farmer and I have an orchard full of apple trees, and I decide to go in with my tractor and pull them all out, that is an irreversible decision. Because it implies that if I pull out all my apple trees this year, I won't be picking apples next year. Because apple trees take time to establish. Apple trees are actually relatively quick. Reversibility with banana trees, I need to wait for 6 years, right, before I can harvest bananas again. So that is an irreversible decision, in the sense that the decision I make today constrains the things I can do next year. The reverse is not true. If I plant banana trees this year, I can, in a few months' time, change my mind and pull them out again, right? And then I've just lost the year. But if I have a capital stock and I destroy it, then that has long-term consequences. And it is only in this case, right, that when today's decisions fundamentally affect the decisions we make in the future, the problems become truly dynamic. If we don't have these sort of intertemporal spillovers, then even though it is a problem that unfolds over time, it sort of becomes a series of static decisions. But it's only when there's true intertemporal spillovers that decisions become truly dynamic. And of course, this applies to climate change, right? The capital that we use to generate electricity is long-lived. The capital that we use in transport is long-lived. And of course, carbon dioxide in the atmosphere is long-lived. And we have the ocean adding further momentum to the problem. So irreversibilities are there in the climate problem. Still, this does not fundamentally affect the difference between decisions under certainty and uncertainty. We need to introduce a second component, and that is learning. Now, we do not know what the future will bring. We do not know what we will learn this afternoon. I have an idea about what I'm going to try and teach you, but we do not know what knowledge we will gain in the future. But we can be sure that as we grow older and wiser, well, older for sure, we will pick up new knowledge. We will know different things in a year's time than we do today. That is something we can be pretty certain about. Now, what does that imply in a dynamic optimization framework? It essentially implies that as time progresses, so does knowledge. And that means that in a year from now, or in a generation from now, people will make different decisions than they would have made had they had the same knowledge as we have today. Decisions will be revised. People will make different decisions because they have different knowledge. And our sort of like idea of what people in 30 years from now should decide is different from what they will actually decide. And if there's a fundamental spillover between our decisions today and decisions in the future, because of the reversibilities in the system, then the facts that we will learn, even if we don't know what we will learn, changes our decision today. And in the following way, what I said was that because of all the uncertainties in climate, because the bad tail is more pronounced than the good tail, we're actually pretty nervous today. Because we face all this uncertainty about what climate change would bring, what the impacts of climate change would be, And because of all that uncertainty, we actually want to be pretty risk averse, and we want to abate a lot of emissions. But people in the future, say 50 years from now, will have 50 years of additional knowledge about climate change, 50 years of additional observations, maybe even more, because we also started to observe other planets, we're starting to push climate records into the past. So they may actually have much more than 50 years of additional observations, and they of course have 50 years of additional climate science experiments, better computers, better models, and so on and so forth. People in 50 years' time will know a lot more of climate change really is than we can possibly do. That implies that people in the future will be able to make more accurate, better, more precise decisions than we can foresee. They will be better able to steer climate policy into the desired direction, and that takes away our concern about climate change. Part of our concern about climate change, because future people will be better equipped to deal with this problem than we are, and therefore we need to worry less about them than we would in the case that there would be no learning. So because we know future people will know different things than we do, even if we don't know what, we actually can relax a little today. I'm going to show you this graph. There's three scenarios. There's two decision scenarios, three possible futures. The possible futures are climate change is a bad problem, climate change is somewhat bad, and climate change is not really something to worry about. And then the two decision scenarios are in 1990, decide for the entire future what to do. That is known as act, then learn. In 1990, decide over the entire future what to do. That is known as learn, then act. Assume that we know that climate change is benign, or we know that climate change is dramatic, and optimize the entire future over that. Those are the dotted lines. And then this other alternative is make a decision now. And in 2010, we know how bad climate change really is. People in 1990 were a bit optimistic about the progress that climate science would make. And then revise your decision as you've learned the true state of the world. And the crucial difference is not so much what happens after 2010, but what is going on in the period 1990 to 2010. These three scenarios are equally likely. So if we just take the average of the three dotted lines, say in the year 2010, when they've most diverged, then where do you end up? Somewhere here, right? You take the average of these three. Whereas if you look at the solid line, we're actually above. We have relaxed. Why have we relaxed? Because in a later year we know what we should be doing, and in two cases we should actually accelerate our program on emission reduction. In the third case we should relax our program on emission reduction. But because we can correct course, we can intensify climate policy as well as relax climate policy, and we know that in the future people will be better able to make the distinction whether or not to do them, or which direction to do. We don't need to worry so much today. We don't need to hedge against the worst possibilities as much, because we know our successors will be more discriminate in their decision making than we can be today. Now this is somewhat paradoxical, and many people don't really get it, but the sheer fact that we know we will learn, even if we don't know what we will learn, should affect our decision making today, right? And that is exactly what is borne out, and in the book there is a numerical example. Final chapter. This is the same Weizmann that we've now seen 3 times, right? First in prices versus quantities, then in gamma discounting, and now in uncertainty. And this is not the only thing. These are not the only things that Weizmann has done. But yes, he is a pretty clever, or he used to be a pretty clever guy. So Weizmann in 2009 wrote a paper that rocked the economics of climate change. And essentially what Weizmann in 2009 says in what we call the dismal theorem is essentially an impossibility theorem, like arrows and footprints. Yes, and what this dismal theorem says is that the uncertainty about climate change is too large to do the sort of stuff that we've been doing now for the last 30 years, that is expected utility maximization. Now, Weizmann does this through a derivation that I don't think is particularly intuitive, so I'm going to here offer you an alternative. So we've looked at the Ramsey rule, which says that the money discount rate R is the utility discount rate rho plus the curvature of the utility function eta times the growth rate of consumption G. And people argue a lot about what rho should be and what eta should be, but there's also, of course, it should be G. And essentially, Weizmann's argument can be upheld with the following consideration. Assume that climate change is so bad that it's going to reverse economic growth. It's going to make us poorer. And G becomes negative. Now, what happens if G becomes negative? Then money discount rate falls, right? One of the reasons for discounting the future is that we expect to be richer then. But if people no longer can expect that, we instead expect to be poorer in the future, then it would make sense to save a lot more, right? We should be content with a much lower return on our investment. If G becomes sufficiently negative, so that eta G is larger than rho, then we're actually in a situation that parts of Europe are now, our money discount rate becomes negative. And then you actually have to pay to put money in the bank, right? Just that you have to pay to lend money to the German government or the Dutch government at the moment. And then they give you money for lending them stuff. You have to pay for the privilege of lending them money, right? Now, if R is negative, that means that things that are further away in the future become more important. Not less important, as you would have if R is positive, that's what we always think about. But they become more important. And the further we look out into the future, the more important things become. And this happens because climate change is pretty bad. So we're looking further and further into the future, things become worse and worse and worse and worse, and we're putting more and more and more emphasis on that. And as a result, we can no longer calculate the expectations. Because the further we look into the future, bigger things become and more important things become, and as a result, everything becomes infinite or arbitrarily large. And if you then calculate the marginal across that, then what you would find, and that is indeed what Weizmann did find, is that if we that should be arbitrarily large, that is, climate policy should be arbitrarily stringent. As I said, this caused a bit of an upset, a bit of a storm. Some people cheered because they thought that the dismal theorem formalizes the precautionary principle. Others cheered because here we had a Harvard professor of economics, no less, arguing for whopping high carbon taxes. So that caused a bit of a stir. Of course, not true. What the dismal theorem says is you cannot do expected cost-benefit analysis. It did not say what to do, right? It just said that the stuff that we've been doing in decision analysis is a lot of crap. And it does not follow from that you have a policy conclusion. In fact, it follows that all your other policy conclusions are false. Now, that the alternative is right. And Weizmann just wrote up an impossibility theorem. Don't do expected cost-benefit analysis on a problem like climate change. But he did not say what to do instead. And the conclusion that we should apply an arbitrarily large carbon tax cannot be. Because what is an arbitrarily large carbon tax and what are the consequences of that? Essentially, that means stop energy use now. And if we stop fossil fuel use now. What happens if we stop using fossil fuels, so we can't make electricity anymore, and that means your smartphone will run out in a few hours, which is pretty bad, right? You cannot heat your home anymore, maybe become very miserable. You cannot grow food anymore, right? You can't grow food without artificial fertilizers. It's very energy intensive. So we should stop doing that, and that means that our stocks of fertilizers will run out in a year or so from now, and it means that next year 7 billion people starve to death. It's not quite true either, because if we can't use fossil fuels anymore, we can't use our water purification services anymore either. And that means that we will run out of drinking water in our cities within the next 24 hours or so. So it's not true that 7 billion people will die in a year from now. It's rather that 7 billion people die within a week or so. So we don't want to impose an arbitrarily large carbon tax, right? We don't want to have a policy conclusion that says it's optimal to kill 7 billion people. So that does not follow from Weizmann, and to his credit, that's also not what he said. That's what the environmental whack jobs that took his work too literally have said follows. Not Weizmann himself. So what do we do if we can't do expected cost-benefit analysis because the uncertainty is too large? Well, the standard answer, going back to Norman Morgenstern and stuff that followed shortly after at Rand and Stanford, if we can't maximize expectation, we should minimize the maximum regret. How does it work, minimize regret? Well, we start by pretending there is no uncertainty. And in every possible configuration of the world, for every state of the world, we find just do your standard optimization, we find the optimum tax. Then we rebase our utility function, that is for each of the states of the world. We calculate all the alternatives to the optimum tax. We calculate the welfare for that, and then we compute the welfare difference between the optimum and all the non-optimal states or non-optimal policies, and we call that difference regret. And then we reintroduce the uncertainty, and then we find across states of the world that tax that minimizes the regret function. So rather than finding the best solution, we're finding a solution that is reasonably good, but we're sure, or rather, we find a solution that is reasonably good and that minimizes the maximum damage that can be done. That's what minimax regret is about. You can't do that on climate change because there's no maximum, right? We're working on the real line. We can definitely work percent. That is what you see displayed here in blue. We're pretending that Weizmann did not write this paper. We're just maximizing net present welfare. Looking on this axis is the carbon tax that we would impose in the near future, and that would then rise to something like with a rate of discount. What you see is that if we have no climate policy, we don't have a lot of welfare, and then if we increase climate policy or increase the carbon tax, then welfare shoots up rapidly and with rapid gains, and then we hit an optimum, and then climate policy becomes more costly than climate change, and welfare starts declining, and the optimum is somewhere there. Minimax regret works the other way around, because we want to minimize regret rather than maximize welfare. We don't know what the maximum is, but we do know what the 50 percentile, the median of regret is. We know that 75% of it, 99 is 1. And if we just focus on the 99.5 percentile or the 99 percentile, this goes here, we actually see a very similar pattern emerge. Namely, that we suffer a lot of regret if there's no climate policy, but then if we impose a modest carbon tax, regret comes down rapidly, but when utility shoots off rapidly, but we minimize regret rather than maximize it. And at a certain point, it turns, and then again, emission reduction becomes more costly. Climate change, climate policy is worse than climate change. And what you see is that regardless of the percentile of regret, you find the same pattern. There are regimes where the cure is worse than the disease, and there's also regimes where the disease is sort of pure and optimum lies somewhere in between. And the pattern of diseases actually hasn't changed. The problem with minimax regret is that you're trying to prevent the worst, but you're not really, you're just minimizing the worst, but you're not really making sure that you get away from the worst. So there's an alternative way of doing this that will actually lead to similar decisions. How would you discover that you are indeed in a Weizmann-like world, where the uncertainty is so large that very bad things may happen after? Now, theoretically, this is equivalent to having a fat tail in your distribution in the sense that your expectation does not converge. What we would typically expect is that if we add observations to our sample, then all our sample moments would converge to their population moments, and essentially, if you add observations, the graph is flatten. So that's what we do here. It's not observations, we use color runs. We add Monte Carlo runs, and we would expect our expected welfare to flatten, right? To converge to true value. It doesn't happen at all, right? It just keeps jumping around. And even if we go from 5,000 observations, already we add one additional observation, and boom, the thing changes again. So we indeed have Weizmann-like fat tails. Now, in fact, did not tell you that this was the number of observations, but I told you instead this is time, then you would say the red line and the blue line and the green line are non-stationary. Now, econometricians would hate me, but you can just apply a stationarity test to this and see what happens, and that is going on here. And we use the augmented Dickey-Fuller test, p-value of the augmented Dickey-Fuller test, and standard, what we would expect is we want to reject the null hypothesis of non-stationarity, and that's what we want to do, and we would want the p-value to be smaller than 1. So here we say the p-values, and what we see as a function of carbon factor being imposed, what we see is again the same pattern, that if we have a zero carbon tax, then we're in a pretty desperate world, and the expected net present welfare is highly non-stationary. Then if we impose a smallest carbon tax, that comes down rapidly, but at a certain point the cure becomes worse than the disease, and the p-value starts inching up again. And if we just want to minimize the fatness of the scale, we should go for this carbon tax. And if you go beyond that carbon tax, then the climate policy that we impose actually causes our tail to get fatter rather than thinner again. And the pattern is again the same. It's little about climate policy, but we can also do too much, and the preferred value is somewhere in between. Now, what we find to be sort of like combine 3 exercises: expected utility maximization, minimax regret, and tail minimization. We find that there's not an arbitrarily large carbon tax, but a carbon tax that lies somewhere in between 50 and 170. You may say that it's a large range, but it's definitely a smaller range than arbitrarily large. So, to wrap up, uncertainty is a reason to be more cautious about climate policy than you otherwise would be. That is true in general. Irreversibility and learning make you actually less cautious than you otherwise would have been. That sort of like dampen the effect of uncertainty. But the possibility of fat tails actually should make you more cautious again, but at the same time should not get you to jump overboard and start switching off all the lights now.